Okay, so today we continue our discussion on the dynamic connectivity problem, and we will see the complete algorithm that gives polylog update and query time. So just to be sure to give you the exact bound, okay. So it will have a query time of login over login and an amortized update time where n is the number of nodes in the graph. Okay. So for the time being, just ignore the specific terms that are mentioned here. Just assume that we want some polylog update and query time. Okay. And now I'm just going to give you the basic framework of the algorithm. We will first study how they maintain this framework in a dynamic setting, and later on only we will get back and see that how this framework can be maintained using ET trees. Okay. So for the time being, do not think of it as a data structure question. Just try to see what the algorithm is doing structurally. Okay. So we are going to maintain log n levels. So there are say log n levels. And each edge, let us say from 0 to log n, has a level in this range. So LE will denote the level of this edge. Okay. Now let us say EI denote the set of all edges whose levels are less than or equal to I. Then we of course have this guarantee, right, that E0 is a subset of E1 is a subset of E log n, and this is equal to E. Next, let us just say that GI is this subgraph induced by EI. So of course we know that G0 is a subgraph of G1, that is a subgraph of G2, and so on, and finally you get G log n, which is equal to G. Now what we are going to do is, for each of these subgraphs we are going to maintain a spanning forest. Okay. So let Fi be a spanning forest in GI. Now the algorithm is just going to maintain two invariants. Invariant 1 says that these spanning forests are contained within one another. And invariant 2 says each connected, it upper bounds the size of each connected component in GI. So each connected component in GI has, say, at most 2 to the power I nodes. Okay, now let's see what's happening. So for invariant 2, you can ignore the spanning forest, right? Invariant 2 does not have any condition about the spanning forest at all. What invariant 2 bounds is just size of a connected component in GI. Now this invariant is definitely true for I equal to log n, right? Why? Because then 2 to the power log n is n. And so if you just set I equal to log n and you notice that E log n is equal to E, meaning for G log n you get G. So in G, of course, any connected component can have at most n nodes. So this is true. Okay. Now if invariant 2 has to be true for, say, I equal to 0, what does this mean? It means that each connected component in G0 has at most one node. That will imply that E0 is empty. Okay. So now these subsets of edges have been constructed in such a way so that you start with an empty subset, then you are adding more and more edges, but in a way that at each level I, the size of each connected component remains at most 2 to the power I. Okay. And now what invariant 1 just says is that f log n is finally going to be f, a spanning forest in G. Okay. So suppose you want to construct a spanning forest in G. How you do this? You start with a spanning forest in G0, which is an empty forest. Then you see that some more edges have been added to E1. So you just augment your spanning forest so that now it spans all the components in E1. Thus you get F1. Then you see that some more edges have been added that are of level 2, that thus you get E2. So then you again augment your spanning forest F1 to include some more level 2 edges so that it becomes a spanning forest of E2. And you go on doing like this till you reach f log n and it becomes the spanning forest of the whole graph. So is this clear? You should be able to visualize what's going on in this thing. Okay. And for the time being, ignore the data structures, ignore how we are going to maintain this thing. Okay. Okay. So now handling and updates. Let's just consider insertion of an edge. Suppose you ask, insert this edge UV. Okay. What you do is, you will deal with it in log n in the highest level itself. So you will how? There will be two cases. Case 1, UV are in same component. How will you note that? You will just probe the spanning forest f log n and ask that whether U and V belong to the same component. If that is the case, then you can just set the level of UV to log n and you don't need to change anything. You don't need to change any of the forest, you don't need to change any other levels, you don't need to change any other non-tree edges. Why? Because just note that all these invariants are still true. Why is invariant 2 true? It's because you did not touch the subgraphs G0 to G log n minus 1. They were not changed. This edge were not part of that subgraph because its level was set to log n. You seem to be a bit confused. Okay, yeah, stop me if you have any question. Okay, so if you are doing this, then you are not touching any of the subgraphs from 0 to log n minus 1. So invariant 2 holds for those subgraphs. And for the subgraph G log n, of course invariant 2 is trivially true because there are log n many nodes, right? What about invariant 1? Invariant 1 is also valid because you are not touching any of the forests at all, right? So none of the forests are changed.
Are you saying AUV to be log n, or you were saying that AUV was log n?
No, this guy is inserted right now, so you have to set its level. So I am just setting the level of LUV to be log n. Okay. Now there is case 2. UV are in different components. Components in G log n. What will you do? Any suggestion? It will also be easy to fix. Yeah. So basically they are in two different components in log n level. Just make it a tree edge, set the level to log n, and just join the two trees in log n level so that you just update this forest f log n. So basically then you just set LUV to be log n and insert this UV again. The levels from 0 to log n minus 1, they were not changed at all because the level of this edge was log n. So this edge did not appear, is not appearing in any of the subgraphs from level 0 to log n minus 1. So you don't need to worry about the invariance there. All you need to worry about is the invariance for level log n. Now we are ensuring that f log n remains a spanning forest because we are adding this edge, and of course we are setting its level to log n, so invariant 2 in level log n is again trivially satisfied. Okay. So insertion can be handled. Okay, we are not looking at the data structure till now, but you can see that insertion should not take too much time. Okay, this is easy. So now we will look at handling the deletion of an edge. Okay.
Number of nodes may increase in the connected component.
Which connected component?
When you are adding that UV edge, you are merging to different components.
Yes, but you only need to look at invariant 2 at level log n, right? And what does invariant 2 say for level log n? That each component has at most 2 to the power log n nodes, which is n.
But now there are n plus 1.
Because the number of nodes remain the same, right? Okay?
So in the operations and insert and delete edges.
Mm-hmm.
So it seems like invariant 2 will when will it get affected?
If you are okay, if there were only insertions, it's not going to change. However, if when we are handling edge deletions, you will see that sometimes there will be edge insertions in some levels I less than log n, and there you need to be very careful.
No, anyway nodes are going to be, they are not going to get deleted. So by nodes you mean vertices only?
Yes. So for invariant 2, if I now just start throwing in arbitrarily some edges in say level Gi, where I is less than log n, of course it will get violated at some point, right? Why? Because GI is just a subgraph with n nodes and some edges. Now I just keep throwing in edges in GI. After some time it will become a complete graph. And of course you cannot say that each connected component has at most 2 to the power I nodes. Okay? Okay. So the more interesting case is delete UV, because if, of course, if there were only insertions, we know that you can just handle this using union find, right? So why will you need this complicated setup to handle this? So we will use this setup to handle the edge deletions, and for edge deletions we will just revert back to the intuition that we had in the last class, meaning that what was the intuition? The hard case was that when you were deleting a tree edge like this, let's say this is small, so you were maintaining a spanning tree, and now suppose this tree edge gets deleted, you need to now find a non-tree edge that crosses these two components, and we will call this, we'll just use a technical term for them. Okay, let's just write it here. We call it replacement edge. Okay, so now we are going to find a replacement edge for this. How are you going to find this? Let these two subtrees be TU and TV, where this edge was UV. Look at the subtree that is smaller. So TV is smaller. So now you just visit all the non-tree edges incident upon TV and try to find a replacement edge. And the argument is that suppose you failed to find a replacement edge, then although you spent much time probing these non-tree edges, yet for each of them there is something nice that is happening. What is the nice thing? The size of the component it belonged to is getting halved, because earlier it was TU plus TV, now it's TV, and this cannot go on for more than log n times. So keep this intuition in mind, and now see how this intuition is being formalized in this framework. Okay. So the first thing is that let us say that the level of this guy is I. Okay. So note that then the trees or the graphs till level I minus 1 and the forests in those graphs, if 0, okay, they will remain unchanged. Right? Why? Because just look at this Gi minus 1. This edge was not appearing in Gi minus 1.
The fact that u comma v which is deleted is in level I is being taken care by the data structure. How do we know that which level it belongs to, it is taken care of?
Yes, that's why I said for the time being ignore whatever is happening at the data structure level. Just try to see how these forests are being maintained and updated by the algorithm. Later on we'll come back to the data structure and observe that these operations can be handled by the data structure. Okay. So now the first thing is that if the level of this edge is I, then of course the subgraphs from 0 to I minus 1 are not affected, right? So you only need to start from subgraph Gi. Okay. Now let us say the easy case. Say UV was a non-tree edge in Fi. What does this mean? UV does not belong to Fi. Okay. then we can simply just delete UV, right? Because then Fi is not getting affected, the connected components in I are not getting affected, and then it will also mean that the connected components in I plus 1 is not also getting affected, right? Why? Because let us see, say this is the forest in Fi, something, so this is Fi, say, something like this. And so this is Fi, and UV was a non-tree edge. What does this mean? It means it was somewhere here within one component. Now if you just look at the forest at some level j, where say j is greater than I, what will you see? The connected components of this forest will be strictly supersets of these connected components. It's as if they have been merged, probably these two got merged and they now belong to Fj. And maybe there was some other component in Fi, these two also got merged, and now these two super components now belong to Fj. So this edge is going to remain a non-tree edge in the forest in J as well. So nothing will get affected in levels J greater than I. Okay, is this clear? Okay. So this case is easy.
There is a non-tree edge in level I. Does that mean it will be a non-tree edge in level I plus 1 as well?
Yes.
Why is it?
It's because how these forests are being constructed, right? So again, just look at this picture.
Because the number of nodes will be increasing in I plus 1, right?
No. The total number of nodes remain the same. It's n at each level. Okay. So you will think of it like this. This is your Fi, and these solid edges are your tree edges, and these dotted edges are your non-tree edges. Suppose from Fi you are going to Fi plus 1. What will happen? You will just see that there are some level I plus 1 edges which were not being considered at this level, and those level I plus 1 edges are maybe crossing some of these components. So you are just going to pick those edges as your tree edges in the next level, and then these three components get merged together. So if there was an edge that was already within the same component, that will remain a non-tree edge in the next level. Okay. Okay. So this case is easy. Case 2, and this is the difficult case. Say UV was a tree edge, okay, in Fi. So then I'll draw the I'll use this to draw some pictures. Okay. Now suppose this was UV, so this was Fi, and suppose this was your UV, and this got deleted. So just look at this tree. This tree is now getting split into two halves, something like this. This is one half and this is another half, right? And now you need to first check if there is a replacement edge. Okay. So the main thing is to how to find a replacement edge, if any. So this is the main difficulty. So first note that since UV belong to this forest Fi, it also belong to Fi plus 1, Fi plus 2 till F log n, right? So all the forests from I till log n are getting affected because a tree edge is getting deleted from all these forests. So the first step is delete UV from all these forests, and the second thing is that find replacement edges for all these forests. This is the thing that you need to do. Okay. Okay, so this step is easy. You can believe that it will just be handled by the data structure. What about this step? To handle this step of finding replacement edges, we will start from the lowest level, try to fix Fi first, and if we can fix Fi, then we will only move on to Fi plus 1 and so on. Okay, so we will move in this direction. Okay, so now suppose we want to find a replacement edge for Fi. The first question is, can the level of that replacement edge be below I? It can or can't?
If an edge is introduced, it is obviously introduced afterwards. I mean, it is not introduced before.
Yeah, so your answer is no, right?
Yeah.
Yes. So the answer is no. Why? Because suppose we are focusing on Fi, right? And we just want to find a replacement edge for Fi. Let's just see how it will go. So the claim is, again, just look at this figure here. Suppose this was your Fi. This was the tree in Fi that contained UV. Okay, this is U, this is V. And suppose, okay, then the level of UV is I. So if you go to Fi minus 1, go to the level below, what will you see? This edge is disappearing. Okay, and then maybe some other edges in these two parts also disappear, but let's just ignore that part for the time being. Now if there is a replacement edge for UV with respect to Fi, that will look something like this, right? Now if the level of this guy was I minus 1, then what would have happened? Yeah, this will be a contradiction, right? Because we have observed that if an edge is a non-tree edge at some level, it remains non-tree edge at all the higher levels. Okay. Let's just start here. So we want to find a replacement edge for UV, and suppose I claim that there is a replacement edge that is like xy and its level is I minus 1. Okay. Okay. So now this edge xy is a non-tree edge in Fi, right? So xy by definition does not belong to Fi. What does this mean? It means this edge xy does not belong to Fi minus 1 as well. Okay. So now let us look at Fi minus 1. In Fi minus 1, this edge UV is not going to be present, right? And that means that these two nodes x and y will be in two different components in Fi minus 1. Why? Because as you are going from fi to fi minus 1, you are only deleting some edges, you are not inserting any more edges. Okay. So now in fi minus 1, these two nodes are in different components, but this edge of level I exists, of level I minus 1 exists, and it is a non-tree edge. So what does this mean? It means that fi minus 1 is not a spanning forest. Is this clear? Okay. So the first observation is that the replacement edge for fi is at level greater than or equal to I. Okay. Now comes the part where you are using the intuition that we just started with. So you start with fi. Okay, so this is say tu, tv, and this is your fi. So uv got deleted, you want to find a replacement edge. So since the tree at v is less, you will start with the tree at v, tv. Okay, and can we say that the size of tv is at most 2 to the power I minus 1? Why is this going to be the case? Because before this edge deletion, this forest was satisfying invariant 2, and it meant that the total number of nodes in tu plus tv was at most 2 to the power I. Now tv is the tree of with less number of nodes, so the number of nodes in tv has to be at most 2 to the power I minus 1. Okay. So the first thing we are going to do is, since the number of nodes in tv is at most 2 to the power I minus 1, what does it mean? We can set the level of all the edges in tv to be I minus 1. What is happening? That only some of these edges, tree edges here, are now part of I minus 1. The remainings are in level I. But if we set all these edges to I minus 1, this invariant is not going to get violated, because in level I minus 1 you will get this tree tv of size 2 to the power I minus 1. Okay. So the first step we are going to do is this: for every edge in, I am writing uv, for every edge in this tree, so this is a tree edge, not a non-tree edge, okay, whose level is I, you do this step, just set it level to I minus 1, and of course update the tree in fi minus 1. Okay. Now this is a step 1. Now what are you going to do is, you come back to I. Here it nothing changed, right? Because in level I you are just looking at the edges whose levels are at most I. So even if you are decreasing some of these edges of levels of these edges, the edges you will be considering in level I remain unchanged. Okay. So now you come back to fi and start looking for replacement edges that are incident upon tv. This was our intuition, right? We will start looking for replacement edges at the smaller subtree. So the second step is, consider all non-tree edges incident upon tv in level I, one at a time. So now when you are looking at one such edge, say y comma x, and since this is incident without loss of generality, check if y belongs to TV. Y has to belong to TV, one of the endpoints. Check if the other endpoint does not belong to TV. If yes, then y comma x is the replacement edge. And what you do, you just insert y comma x So let's look at this step first. So you are iterating through all the non-tree edges incident upon TV, and you are looking at one such edge yx. Without loss of generality, y belongs to TV, and suppose that you have found that the other endpoint does not belong to TV. Then by definition the other endpoint has to be in TU. It cannot go to some other component, right? Because the initially Fi was a spanning forest in GI. So xy is the replacement edge. You have found it at level I, and the level of what will be the level of this guy? The level of this guy is at most I, right? Okay. So now suppose you just insert this guy into all the forests from Fi to F log n. The claim is that then this fixes everything. Meaning if you have found a replacement edge for Fi, that will also be a replacement edge for Fj for j greater than I. And why is that? Because these forests are contained within one another. That is the reason. So basically, if you just compare Fi and Fj, to just harbor this point a little bit further, so this is Fi, and if you are going to Fj, you just added this intra-component edges, some intra-component edges, merged some component and got Fj, right? So to go to Fj, you added these dotted edges. This is what I mean. And now in Fi, one of these components were getting split because you were deleting some tree edge from here. Hence in Fj also this giant component got split, right? But to fix Fj, it just suffices to fix this tinier component in Fi that got split, because what this replacement edge is doing is just going to patch up these two components. So you don't need to go individually consider Fj anymore. Is that clear?
What if I mean, we have a replacement edge that is not between TU and TV, but is going through some other component?
That cannot happen. Then it means that in Fi itself, your original spanning forest was not spanning at all. Just look at the union of TU and TV. That was one component, right? Okay, let's consider this case. How can it happen at some upper level? So, okay, first let's just look at level I. So, this is your TU, this is your TV. Before this edge was deleted, in Fi this was just one component, and Fi was a spanning forest. So, the claim is that no edge incident upon TU and TV can go outside of this component. Because if it were going outside of this component, Fi itself was not a spanning forest. This was not a component at all. So the point is that when you are iterating through all these edges incident upon TV, there are only two possibilities. One, you are finding that both the endpoints are in TV, Or 2, you are finding that one endpoint is in TV and the other endpoint is in TU.
Some upper level can be there is some tree edge for some other upper level.
Hmm?
You had 3 components in some upper level which were connected into a same forest. Now one of the component is breaking up into TU and TV,
Hmm?
but TV is connected to something else and TU is connected to something else, and between those two there is some tree edge.
Can you draw this thing in the board? I got lost. What you are trying to say? Because as you are going to the upper level, what is happening? You will just be merging some of these components to get a more larger component. It's going to be a strictly laminar structure. Yeah, just come to the board and draw this thing. Just 1 second.
Can it be like this? Like you have this component which
Mhm.
is U and V,
Mhm.
and then you have something else here.
This is in FI.
This is in if j greater than I.
Okay.
You have something here. Now there is a non-tree edge. It can be so
What is the level of this non-tree edge?
j. Like say if this is L of t is equals to j.
It cannot happen. Why? Because Fj is a spanning forest in that level, right?
Yeah. So
Oh, okay. So, okay, fine. This can happen. Fine. Then.
now if you may not find a replacement edge here, but this will fix this large component, right? Now this thing is breaking.
Yeah. Okay. So, what you are saying is that there are other ways to fix Fj.
Yeah.
That I agree with. Of course, there are other ways to fix Fj. But what I am claiming is that if you just fix this component UV, if you can patch up this component UV, you do not need to look for other ways. Do you agree with that? Is this clear? So, if you patch up this tinier component, you don't even need to look for these replacement edges because you know that you have patched this thing up. Okay? Okay. Okay, so now this is the best case scenario. What is the worst case scenario? You just probed such an edge and you found that X also belongs to TV, right? So now comes the intuition. If no, what will you do? You have done some redundant work. You ought not to have looked at that edge. If you are in this scenario, then you have actually found your replacement edge and you just make log n insertions to this forest and you stop, right? So, and stop. By stop, I mean just exit this while loop altogether. Nothing else to be done. But what is the bad case? The bad case is that you have seen an edge, but it's not a replacement edge. So, you did some constant amount of work to find that edge through your ET tree, constant or log n, but it is not helping you at all. What will you do?
Go to the higher level and check if the trees are merged in some higher level. I mean,
Yeah, that you need to do. I mean, what you are saying is that suppose I iterate through all the non-tree edges incident upon TV and do not find any replacement edge. What does this mean? I mean, the forest in Fi is fine. It cannot be patched up. But it still might be the case that Sangyukta pointed out, that in forest Fj you might find a replacement edge. So, you need to go to that higher level. Okay? But the point is that in level I itself you are doing lot of redundant work, right? You just probed all these edges and there can be many such edges. You don't know how many of them are there. I mean, TV times Tu. No, not TV times Tu. TV square. In the worst case, there can be TV square such edges.
you were saying that how do you actually differentiate between cross edges and edges that are belonging to the same component?
Yeah, there is no way to distinguish between them because ET trees will only give you the edges incident upon TV. ET trees cannot give you the cross edges. Okay? The point is that how you account for this work. You have to do this work. I mean, there's no getting away from it. Okay? Okay, the answer is simple. If no, just decrement the level of that edge by 1. Now why are you doing this? Because look at step 1. In step 1 we have ensured that this tree TV is now a tree in level I minus 1. Okay? And here we are seeing that xy has both endpoints in TV. So xy can both feasibly be a non-tree edge in level I minus 1. Nothing will get violated because this invariant just says that if I minus 1 has to be a spanning forest, which is the case. Okay? And while we are doing this, we have ensured that invariant 2 is also satisfied because the size of this tree was at most 2 to the power I minus 1. So if we decrement the level of this edge by 1, meaning by setting it I minus 1, by setting it to I minus 1, then the forest in level I minus 1 is not going to get affected. Okay? But why is this helpful? This is helpful because of our initial intuition that you are probing this edge and it turns out to be a failure, but when this happens you are decrementing the level of an edge. Earlier the level of this edge was I and now it is I minus 1, and in I the upper bound on the maximum size of a component was 2 to the power I, whereas in I minus 1 the upper bound of a maximum size of a component is 2 to the power I minus 1. So during its lifetime the level of an edge can only drop, and this is also the principle of monotonicity that we are seeing here, and it cannot drop by more than log n. So although it's a fully dynamic setting, the framework has been set up in such a way that the level of an edge can only drop. Okay? And so this is basically the algorithm. So this is how you deal with level I, meaning when you are looking for a replacement edge at level I, and if you fail to find a replacement edge at level I, what will you do? You will just go to level I plus 1. And what will you do at level I plus 1? See, earlier this edge UV that is being deleted was a tree edge in level I plus 1, right? So just look at TU and TV in level I plus 1. That will be slightly larger components, and try to find the replacement edge at that level. If again you fail, you go to level I plus 2 and so on till you reach level log n. And if you fail to find a replacement edge at level log n, what do you say? You say that actually the graph is splitting up into 2 components. Okay? And now finally what you need to check is that the data structure part. So you can see how the running time will be analyzed. We will say that the data structure is doing some work only when it is accessing an edge. Okay? So let's just look at it step by step. Insertion. Okay, what will be the data structure first of all? Let's just write down the data structure. So for each level I, you store this forest Fi as a AT tree. Okay. And now we need to find the replacement edges as well, right? So we need levels of the edges to find the replacement edges. So basically, treat each non-tree edge in GI as a token of value that is equal to the level of that non-tree edge associated with its two endpoints. So basically this is, you are maintaining this Fi as an ET tree, and with each node, if there is a non-free edge associated with it, you have a token, and the value of that token is that level of that token, that's it. Okay. And additionally, you will have a different type of token. There will be two type of tokens. One is this, and the other one would be, treat each tree edge as a token as well. So this is for non-tree edge, this is for tree edge. Why will you need this? This is because in step 1, you clearly want to identify the tree edges at level I. It will be too much of work if you go through all the edges in the tree, and you see that many of those edges are already at level I-1 or below, and you are not doing anything. For that, you need these type of tokens. Now let's just look at the total work that is being done. So for insert we are just dealing with it at level log n, right? And you can see that it's basically at most you are just making one insertion into the ET tree data structure at level log n, or constantly many insertions. So this will be worst case log n time. Okay. And for delete, what are you doing? You will say to account, okay, if a non-tree edge is getting deleted, then this is easy in the sense that this is just going to be log n time. Why? Because you have to delete it from at most log n levels. The interesting thing is that when a tree edge is getting deleted, and then you account for the work by saying that the total work done by the data structure is proportional to, up to a log n factor, is proportional to the number of edges it is accessing, the number of times it is accessing an edge in some technical sense. Now, when is it accessing an edge? It's accessing an edge either at step 1 or at step 2. Now, when it is accessing an edge in step 1, immediately it is decrementing its level by 1. And similarly, when it is accessing an edge in step 2, either it is making it a tree edge, this part, it is making it a tree edge and making log n insertions and stopping, or it's decrementing its level by 1. So basically, if you want to amortize the work done in this fashion, you will just look edge by edge, and the lifetime of an edge looks like this. Each time the data structure accesses it, either it becomes a tree edge, case 1, this is this case, and if it becomes a tree edge, then this event cannot happen any more, right? I mean, once a node becomes tree edge, an edge becomes tree edge, it remains tree edge till it gets deleted completely. So this type of event can happen only once. Otherwise, all the time, regardless of whether it's a tree edge or a non-tree edge, the moment data structure is accessing it, its level is being decremented by 1. So for each edge per edge, we are doing log n square work, because the number of level decrements is log n, and for each level decrement we need to do log n work to update the ET tree data structures. So this is a monotonicity principle again, and we are using this with the high level intuition that we started with, that basically we want to have this thing that one giant component is getting split up. When we are searching for a non-tree edge, we want to ensure that if this is a bad probe, then the component it belongs to is getting halved. Okay. So that's why the update time will be log square n and the query time will be log n over log n. Why? Because in ET tree, suppose you have two nodes UV, and you are asking whether they belong to the same tree or not. You need to go to the root, right? So if you implement it trivially as a balanced search tree, you will incur log n time, because from each of these two nodes you need to go to the root, and the root might be log n distance away. However, if you implement it as a B trees, you can improve this bound slightly to get log n over log n time. Okay. So this actually completes the deterministic polylog n update time algorithm for dynamic connectivity. Next week, what we will see is a randomized algorithm for dynamic connectivity that gives polylog n worst case update time. So here this is amortized, right? How to make it worst case update time using randomization, and that will also use the random sampling framework. Okay. Okay, so let's stop. Next class is Tuesday, 11:30. Oh, Tuesday is a holiday, so the next class is Wednesday at 11:30. Wednesday is not, right? Is it or is it not? Let's just fix this. Why is it a holiday on Tuesday? Oh, Republic Day. Okay, no, that's fine. So Wednesday.